And we are live. Welcome back to Algebra with Doug, sometimes known as Algebra with Dog. Okay, so my beautiful assistant Mocha and I are ready to teach you algebra. Well, I have to confess that I often make fun of Mocha a little bit by saying that she's not very good at this type of math, not very good at that type of math, as if dogs can't do math. And, you know, she doesn't complain because the thing that's nice about dogs is they never say anything, so they can't complain. But she really surprised me this morning because I looked in her crate. She has a crate, the travel crate, but we keep the door open all the time and she likes to sleep in there sometimes. And I went in there and I found this. Huh? Wow. So she has some surprises in store for us. I think she intends to become a teacher in these lessons and eventually she may make me obsolete. But for now, I know she hasn't finished the book yet, so I don't want to put pressure on her and make her teach this week's lesson. And for that reason, I am going to go and release her upstairs. I will be right back, and then we'll get into our math lesson. And I'm back. Okay, so this is the Highlanders. That's a rugby team from New Zealand. And that's the usual preamble. I like to talk about my dog and talk about the weather. The weather is kind of nothing much to say. Let's get into the math. The math is why we're all here. I want to do some review to start with. It's always a good idea to review some of the things we covered last time. So absolute value. The absolute value of negative 10 is equal to 10. The absolute value bars force whatever is inside to become positive. If it's negative, it becomes positive. But what if it's already positive, like this plus 10? I wrote the plus sign. You don't have to always write that, but I wrote it. The absolute value of positive 10 is also equal to 10. It doesn't become negative. Whatever is inside the absolute value bars has to be positive. And that does some interesting things when we do algebra. So we'll get into that a little bit. Here's another review. A very simple statement, the absolute value of x equals 1. How can we solve this? Well, we know that the absolute value of 1 equals 1 because we understand this, but we also know that the absolute value of negative 1 equals 1. So that means x is equal to 1 or x is equal to negative 1. These are the only answers to this particular little question. And I can even graph that on the number line by putting closed circles on both 1 and negative 1. The number lines are really helpful for us to visualize our answers when we do this type of algebra. So that's a little bit of an easy one, and we covered some stuff like that last week, but we're going to do a little bit more review. I'm going to do some erasing. Okay, my next example. Absolute value of x, and this time we have an inequality, is greater than 3. Now we definitely did a bunch of these last time, and this is getting to be a bit of an easy one. A lot of the students will also always realize, okay, therefore the answers are going to be 3 and all the numbers bigger than 3, but also negative 3 and all the numbers less than negative 3. When I have the greater than symbol, that's what tends to happen. I have two areas with answer on my number line and my answer. But how did we figure that out? We figured it out by plugging in some values. So if we plug in, for instance, 2, the absolute value of 2 is 2. Is 2 greater than 3? No. So this is not one of my answers. And that's one of the things that tells me I can get started with my number line. I'm going to show 0. I'll show 3 and negative 3. And of course 2 is here. But it's not true. So 2 is not part of my answer, and that makes me realize, okay, yes, I was right before when I thought what I need to do is put circles on the 3 and the negative 3, and it's going to be the region outside of these that we shade. You can use an arrow, or I can use a dot, dot, dot to show that I know that it keeps going. So this is a pattern that we learn to realize. When it's a greater than symbol in a situation like this, we're going to be shading on the outside of the two numbers where we put our circles. It's not greater than or equal to, so I have to keep an open circle to prove that I know that 3 and negative 3 are actually not answers. And of course I can plug in several more values to test this. I can plug in values that I know are in the area I think is going to be in the answer, and I expect those to verify. I can plug in values that I know are in the area I don't think is part of the answer, and I expect those to not verify. But once we realize the pattern, we realize what we can do. We can take this statement and we can write x without the absolute value bars is greater than 3, but we can also write x without the absolute value bars is less than negative 3. So when I do that, I'm showing the symbol pointing in the other direction, but I'm also changing the 3 to a negative 3. But when you realize that this is the right answer to this thing, well, this makes sense. And being able to do this is a really useful step when we're trying to simplify and then graph an inequality like this one. So that's a good little example, and that is a bit of a review. I'm not going to be doing much plugging like this. We're going to be working with the idea that we already understand that we can do this. We can split our inequality into two inequalities that don't have absolute value bars. We just have to be careful how we do it to make sure we remember how to arrange the symbol and when we change the number to a negative number. So let's do another one and take that approach. Okay, my next example, I want to change a few little things. I don't want to always have x, absolute value of x greater than number. So how about absolute value of x less than or equal to? So now it's a less than, but it also has the or equal to. And if I understand what I'm doing, I'm going to put in my number, which is a 4. Then I'm realizing, okay, this time, because it's less than, I expect to be shading in between the two numbers where I put the circles. And because it's or equal to, I expect to shade in those two circles so that they're solid circles to prove that I know that those two values are part of the answer. In a way, we're tempted to just jump right to our final answer, but I don't think we should jump quite so quickly. We want to show how we know. So what do I do here? I hinted at that last time. I write x less than or equal to 4, writing it down the same way except I don't have the absolute value bar. But I also write x greater than or equal to, reversed symbol, and negative 4. And does that make sense when we think about how we're going to graph? Well, yes, we were expecting to put circles on two numbers and shade in between them, and that's what's going to happen here. So I'm going to show my 4, and I'm going to show my negative 4. I'm putting circles on both of those. Interesting how I keep on putting circles on that number and the same number except negative. Will it always work that way? Well, no, actually. We'll see examples where it's not necessarily going to be a 4 and a negative 4 every time. But let's get there. We also expect to shade in between them. Does this make sense? The values that are less than or equal to 4, well, yes, they'll be over here, shading to the left of the 4. But the values that are greater than or equal to negative 4, that's also here. We're shading to the right of the negative 4. So we're shading in between these. And because of the or equal to, we're filling them in. So it would be nice if we could just do millions of examples just like this one, because it is easy and it is kind of fun. Especially fun because we get to draw a graph. I'm going to get rid of this piece of chalk. And I'm going to get a new piece of chalk. And look at my next example. So still we were all of what we have done is a review. It's just that we're showing how we treat our inequality a little differently. We're sort of jumping into this because we understand it now. That's the idea. But there are all sorts of interesting different things that can happen. So we're going to try a bunch of these different things and see what the algebra gets us to do. I'm just keeping an eye on my time. Okay. My next one . Not much more challenging, just a little baby step. How about the absolute value of x greater than or equal to, and we have negative 1. Okay, so what's different? I went back to a greater than, but I kept the or equal to. You have all this variety of less than or equal to, or greater than or equal to. But you have learned, because you've done a lot of practice, that the or equal to just determines whether or not we fill in those circles. And the greater than or less than determines whether we're shading on the outsides of the two numbers or the in between the two numbers. And we start getting a feeling of comfort with this, which is a good thing to have. Now, this is negative. I hadn't done any examples before where I had a negative number there. And that forces us to slow down and think about what's happening. And it also tempts us to just jump to an answer, and that it's good to think about what we think the answer is going to be, but it's also good to take our time and show the steps and make sure that we feel comfortable that we have figured out the answer. I'm going to start by drawing my number line and putting my 0. I always like to show that 0. And I see -1, so I think that -1 might be involved in my answer, so I'm going to show it. 1 might also be involved in my answer, so I'll show that as well. Not sure whether I need to specifically show any other numbers on the number line. It's a greater than. So greater than usually means we're shading on the outsides of the two circles. But I'm not really sure where to put the circles. I feel pretty confident I need a circle here on -1. It's a little different. I didn't change very much, but it still became a little different, and I want to slow down. I think what I need to do is I need to show my splitting into two inequalities that don't have the absolute value like I was doing in the previous examples. So we have x greater than or equal to -1, just like it was written, except without the absolute value bars. And then we'll write x less than or equal to, and I'm putting the negative of this number, but the negative of -1 is +1. And then, am I sure that this is right? Because that was a little weird. Do I feel sure? Well, I can sort of test it. A number greater than or equal to -1, like say 0. Is 0 going to be true here? The absolute value of 0 is 0. Is 0 greater than or equal to -1? Yes, it is. So that makes sense. A number less than or equal to 1. How about -3? -3 is less than or equal to 1. If I put -3 in here, -3, the absolute value of -3 is 3. And 3 is greater than or equal to -1. And that's where the leap of logic sort of intrudes. And I say, but wait. The absolute value of everything has to be greater than or equal to any negative number. The absolute value has to be positive. And all positive numbers are greater than any negative number. So that makes it sound like, do I need circles here? Or do I shade in everything? Well, what I'm going to do is I'm going to shade it in the way I'm used to doing and see what it looks like. Greater than or equal to -1. I'm putting a closed circle on -1, and I'm shading this way because this is where the numbers greater are. And I'll show ... that it keeps going. But I also need to shade less than or equal to 1. Well, that would normally make me put a closed circle here, so I'll put it. And then I'm shading here where it's already shaded, but I also have to shade all here. And the answer is, well, yes. I'm shading everything. My number line answer is a number line where everything is shaded, because all numbers that we could possibly put in here, once we do the absolute value to those numbers and they become positive, well, they have to be greater than negative numbers, so every number works. I don't really need to show the circles, but I don't think it's wrong to have them sitting there, so there's my answer. So this is one of those interesting little experiments you do, where you do something a little different as a way of testing whether what you've been working on makes sense, and this seems to make sense. I like this example. All right, I think I got to the end of my first page, so I'm going to take it off of my clipboard and take a look at what's next. Now we're starting to put a little bit more inside these absolute value bars. That means I need to erase, and when I erase, of course, that's a good time for the students to get up and stretch their legs or whatever they have to stretch and get a sip of water. I think I'm going to be getting a sip of water as well. And that reminds me when I get upstairs to make sure that Mocha has some water. She did this morning to make sure that she still has some. Okay, that's good. Very refreshing. How about this one? The absolute value of x plus 3. So we can put more in there than just an x. X plus 3. Greater than 2. How am I going to treat this? I'm going to split it into the two simpler, if you will, inequalities that don't have the absolute value bars in them. So I write x plus 3 greater than 2, and I write x plus 3 less than -2. I keep doing this thing that I already know works. And then I do a little bit of algebra. And you know with algebra, when you have an inequality symbol, you do the same steps that you do if there's an equal sign. You just have to be careful if you're dividing or multiplying by a negative number, but we're not doing that in this situation. So I'm doing x plus 3 minus 3 is greater than 2 minus 3. I'm showing all my steps. I'm subtracting a 3 from both sides so that I can cancel these. My x is isolated. 2 minus 3 is negative 1. I have x greater than negative 1. Over here, I am subtracting a 3 from both sides as well. These cancel, x is isolated. Negative 2 minus 3 is negative 5. And something wonderful and magical has happened. These two numbers are not just the same number, one positive, the other negative, like has happened in all these simpler examples. Why? Why did that happen? Let's draw our number line. I'm going to put a 0. I need to show a negative 5 and a negative 1. Oh, that's way over here. Well, that's okay. I'll put negative 1 here. I'll put negative 5 here. Now I want to graph these. Greater than negative 1. Open circle shading over here where the numbers that are greater than negative 1 are. And it keeps going. Less than negative 5. I need an open circle and I shade to the left. And I put dot, dot, dot. It keeps going. So with greater than, the same thing as usual happened. I have the two dots and I'm shading on the outsides of the dots. But because of this plus 3 being inside here, it sort of moved the two numbers so that they're not negative 5 and positive 5 or negative 1 and positive 1. They're negative 5 and negative 1. And there's nothing wrong with that. It's just what happens when you have this type of an inequality that you start with. So that's cool. It adds some interesting variety, and yet all the tools that we've been practicing still work to get the answer. I'm going to move on to the next example. I have a bunch of examples where we do something slightly different here, something slightly different there. And that's how you get a feel for this. Making sure that you feel confident that you're able to do the questions by trying all sorts of different combinations. How about absolute value of x minus 4 less than or equal to 8? So I keep juggling that if it's less than or greater than. I keep juggling that is it or equal to or not. And I'm juggling what's in here. I added something inside with my x the last time. Now I'm subtracting something inside. I make little changes, but I'm not making big changes. This gives me x minus 4 less than or equal to 8, and x minus 4 greater than or equal to negative 8. Notice how I slow down when I do that, because when you're doing something that matters, it's a good idea to slow down and make sure that you don't forget. Okay, now I'm doing some algebra. X minus 4 plus 4 is less than or equal to 8 plus 4. Cancel, cancel. X is less than or equal to 12. X minus 4 plus 4 is greater than or equal to negative 8 plus 4. Not very different. I'm just adding a 4 to both sides in both of these. These cancel. X is greater than or equal to negative 8 plus 4 is negative 4. So the numbers are a little different again. This time we have a positive 1 and a negative 1. And they're not both 4s, they're not both 12s, but we were expecting that because we started to understand what happens when we do this. I will graph on the number line. Negative 4 and 12, so I'm going to put my 0. I'll put negative 4 here. I'll put 12 way over there. Less than or equal to 12 means that I am putting a solid circle on the 12 and I'm shading to the left of it. Should I go all the way to here? Do I dare to go all the way to here, or am I sure? I am pretty sure, but I'm still going to take a look at this. Greater than or equal to negative 4, solid circle on negative 4, and I'm shading to the right of it. So yeah, I could have shaded all the way to that negative 4. I have an answer. It's not a very surprising answer. We had a less than symbol, so we are shading in between. It's or equal to, so we have solid dots. And something extra happened in here, so we have numbers that are not just the positive and negative versions of the same size number. This makes sense, and when it makes sense, I feel confident in it. Let's do some more. How am I doing for time? I'm doing quite well for time. Not really sure exactly how long this week's lesson will be. I usually aim at making them an hour, but I don't think I should always be trying to force that to happen. It has to be exactly an hour. We'll see what happens. How about the absolute value of 3x minus 1? Now I'm subtracting a 1 inside the absolute value bars, but I'm also multiplying x by 3, so I'm juggling it again a little bit more. But, oh, I have an equal sign. Can you predict what's going to happen that's different from the last few examples because we have an equal sign? Yes, I think you can predict it. I'm not going to give it away just yet. How do I proceed? The same way. I split it. I have 3x minus 1 equals 11, and I have 3x minus 1 equals negative 11. Yeah, that's working. So the symbol doesn't turn backwards, or does it? We could say, well, sure it did. An equals, if you write it backwards, still looks like an equals. So when it's an equal sign, we don't have to turn the symbol backwards, or it doesn't matter if it's backwards, whichever way you prefer to think it. But we do have to put 11 and negative 11. And then we have to do our algebra. So we're using the same steps we've been practicing. 3x minus 1 plus 1 equals 11 plus 1. These cancel. 3x equals 12. Divide both sides by 3. X equals 4. Didn't write that very big. X equals 4. Interesting. I'm going to start drawing my number line. I don't want to put the labels yet until I see what I'm getting from this one. 3x minus 1 plus 1 equals negative 11 plus 1. These cancel. 3x equals negative 11 plus 1 is equal to negative 10. Divide both sides by 3. Whoa, something different is happening. These cancel. X is equal to negative 10/3, which is a perfectly good number. It's a fraction. Do I have to turn it into a decimal? No, I don't. But I could. Negative 10/3 is negative 3.33 in a rounded off decimal. That's fine, but of course negative 10/3 also works. So I need to graph these. I want 4 to fit and negative 3.33 to fit. So I'll put a 0, put 4, I'll put I made that piece of chalk too long. I'll put negative 3 here. In fact, I'm even going to put, not very proportional. I think it's good enough. I'll put negative 4 there. It's a little bit of a sloppy number line, but I'm going to forgive myself for that because this number is in between negative 3 and negative 4. So how do I graph that? It is equals. I don't need shading. But 4 is one of the answers, so I need a closed circle on 4. And then negative 3.33, how am I going to show that? I'm putting a closed circle a third of the way between negative 3 and negative 4. But I didn't relabel it, so I just feel like I want to say negative 3.33 with an arrow, just to make it clear. I know that I know what the answer really is. If your graph isn't as tidy as it could have been, well, this is a way of letting it be known. Okay, well, this is what I was trying to show. I think this graph is pretty good, though. So we got something different happened. Because it's equals, we just have 2 dots. We're not too surprised by that. Because we have all sorts of extra stuff happening in here, it's not just a 4 and a negative 4 like that, or a negative 3.33 and a positive 3.33. We ended up with 2 different looking numbers. The fact that one's positive and one negative happened because of what we have, but it doesn't have to be. We've seen an example where both of the dots were on a negative number. So the only other thing to mention is, well, we got a decimal. Why did we get a decimal? Just because of the algebra that happened. Because of the sizes of the numbers. This 12 divided by 3 perfectly, but this negative 10 divides by 3 and you get an answer that's a decimal. Nothing to be afraid of. We know how to handle decimals or fractions. So if I want to label this dot as negative 10/3, well, that's correct as well. In fact, it's a little bit more correct because I didn't have to do any rounding. Or I could label it as negative 3 and a third if I want a mixed number. This is actually just kind of fun. Bit messy though. Okay, so I'm going to move on and do another example. And again, I'm going to try to change something. I'm going to try to do something a little different every time. And I will take advantage of the chance to stretch my shoulders. This is like stretching my brain. I just can't reach my brain. Okay. Refreshed, he moves on. Okay, our next example is the absolute value of x plus 6, the plus 6 is not inside the absolute value bars, equals 14. what should I do? What I need to realize is that I can do some regular algebra to this to simplify it before I worry about the absolute value. Do I need the absolute value part of it to be isolated on one side of the equals? I would say yes. So that means I'd like to move this 6, move it. I need to subtract the 6 from both sides so that I can cancel this 6 and change what's on the other side. Let's try it. This is just regular algebra steps that we've been doing for a while. These cancel. Now I have absolute value of x equals 14 minus 6, which is equal to 8. And it goes back to being similar to some of the ones we were doing last time and earlier in today's lesson, that it's kind of a simple one. All that's inside the absolute value bars is the x. I split it and I have x equals 8 and x equals negative 8. And we're back to that where it's the same number, but we have a positive 1 and a negative 1. So we can graph this. Negative 8 and 8, that's right. I put solid circles on both of them. They're my only two answers. It makes sense. So this seemed like a really crazy, interesting, different thing to do, but it actually isn't all that different. It's not very different from what we've been doing for a while. We use the skills that we've known for a while, and we turn it into something simpler and easier. Okay, so I'm going to move on to my next one now. Let's see what else we can do with this. Okay, how about 5 times the absolute value of x equals 20? Now this is on the outside again. I want the absolute value of x part to be isolated on one side of the equal sign. So I'm going to divide both sides by a 5. These cancel. This is now isolated. 20 divided by 5 is equal to 4. It happened again. I thought I was doing something clever and interesting, but it ended up being just an extra step of simplification that's done right away. And then we're able to do our split. X equals 4, x equals negative 4. On the number line, let's get some chalk. Put a 0, put a negative 4, put a 4, and those are my answers. I put solid circles on both of them. I'm finished. I want to do some verification. If I plug into the original equality, the original equation, which was this, it's hard to see it anymore over here, so I'm writing it again. Okay, if I plug a negative 4 into this, well, the absolute value of negative 4 is 4, and 5 times 4 is 20, it's working. And if I plug positive 4 into this, well, the absolute value of 4 is 4, 5 times 4 is 20, it's working. So I feel confident that this is the right thing to do. Okay, well, that's fun. There's an extra step involved, that's all. How about, okay, I can see what I'm doing with my next example. It's a little bit interesting. This Doug, he just likes taking slight little baby steps. I don't know if Mocha will be trusted to do that when she becomes the teacher. Will she be doing baby steps, or will she be showing off how fast she is with the 4 legs and all that and going too fast for the students? Don't know. We'll see what happens when she finishes that book. How about negative 2, make that negative sign bigger so you can see it better, times the absolute value of 3x. Okay, equals negative 16. I'm going to divide both sides by negative 2 because I want to isolate the absolute value part of this. If this was an inequality symbol, I'd have to be careful what I do because I'm dividing both sides by a negative number, but this is an equal sign. So this negative 2 cancels with this one. My 3x in the absolute value bars is isolated. Negative 16 divided by negative 2 is equal to positive 8. This isn't so weird or so wild. I divide this into 2, I split it into 2, and I have 3x equals 8, but I also have 3x equals negative 8. Finishing the algebra, I get x equals 8/3, and I get, finishing the algebra, I get x equals negative 8/3. Notice how I didn't switch it into a decimal this time, because I am not afraid of fractions. Drawing my number line, I'm putting a 0. I want to show 8/3 and negative 8/3, but will I label those? 8/3 is in between 2 and 3. So I'm going to label 1, 2, 3, negative 1, negative 2, negative 3. I'll label them. 8/3 is going to be 2/3 of the way between 2 and 3. So it's going to be about here. And I put a solid circle because it is an equal sign. And then negative 8/3 is going to be here. And if there were any doubt about what I mean by where these dots are and that aren't labeled, I can just label them if I want. I have my answer. It's not so weird. We ended up with a fraction or a decimal, and it doesn't matter because we already know how to deal with those, and we know how to do all this new stuff as well. That's interesting. And I got to the end of another page. What's next? Okay, more of them, but we kept on doing these special ones where we did some extra stuff with an equal sign because it was something new. So let's do it with the equal sign. There's a little bit less stuff that can happen. I think it's time to do a few of these with inequality symbols and not only with equal signs. At least a couple of them. I see a couple of them in our future. Okay, I got to the end. Yeah, that's the page I got to the end of. I'm going to put it over here. And I'm going to check how I'm doing for time. I have to add, because I now have 2 video clips that I'm going to have to put together, I have to add the times in my head to make sure I don't make this lesson 7,000 hours long by accident, just because I'm having so much fun. Okay, absolute value of 2x minus 8 greater than 6. Okay, we have extra stuff inside the absolute value bars, but we don't have extra stuff on the outside of them. So we are able to go right into our split. It is a greater than sign this time. So we have 2x minus 8 greater than 6, and we have 2x minus 8 less than negative 6. See how I slow down? The key moment. Okay, I am going to add an 8 to both sides, and I know I'm going to end up doing that over there as well. These cancel. 2x greater than 14. Not finished. Divide both sides by 2. X is greater than 7. Interesting. Interesting. Yes. Now, I divided both sides by positive 2. I do not have to flip the symbol. Here, 2x minus 8 plus 8 less than negative 6 plus 8. Cancel, cancel. 2x less than negative 6 plus 8 is 2. Divide both sides by 2. Cancel, cancel. No need to flip the symbol. X is less than 1. X is less than 1 and x is greater than 7. That's interesting. Let's graph it. I have 1 and 7. I'll put my 0 over here. There's my 1. And there's my 7. Greater than 7. Open circle shaded to the right. Dot, dot, dot. Make my chalk longer. And the other one, less than 1, open circle, shade to the left, dot, dot, dot. Those look like dots now. Okay, so interesting. We have that thing happen where it's the 1 and the 7. It's not a 1 and a negative 1 or a 7 and a negative 7, and that happened because we have extra stuff happening in between our absolute value bars. It's interesting. Verifying. Let's try plugging negative 1 into this. 2 times negative 1 is negative 2. Negative 2 minus 8 is negative 10. The absolute value of negative 10 is 10, and 10 is greater than 6, so it's in the shaded area. It makes sense. How about trying something in the unshaded area that should give an answer that's wrong? How about 3? 2 times 3 is 6. 6 minus 8 is negative 2. The absolute value of negative 2 is 2. 2 is not greater than 6, so I should not be shading it, and I didn't. That's good. How about trying 8? Should give us something that verifies. 2 times 8 is 16. 16 minus 8 is 8. The absolute value of 8 is 8. And 8 is greater than 6. It makes sense. I trust it. I like it. It's fun. So the greater than, less than symbols, now that we have this extra stuff that's not slowing us down, we learn how to handle all these different things one by one, and eventually we can handle all of them at once. We're good. We're getting really good at this. Okay. Okay, I had 2x minus 8 inside the absolute value bars the last time. How about if I have negative 2x minus 2, lots of negative signs this time, greater than or equal to 4. Split. This is all that's over here on this side of the inequality symbol is the absolute value, so I don't have to simplify first. I'm going to do my split. Negative 2x minus 2 greater than or equal to 4, and negative 2x minus 2, slow down Doug, less than or equal to negative 4. Algebra, negative 2x minus 2 plus 2 greater than or equal to 4 plus 2. Cancel, cancel. Negative 2x greater than or equal to 4 plus 2 is 6. Nearly there. Divide both sides by negative 2. Cancel, cancel. X is isolated. This time I divided both sides of an inequality by a negative number, so I have to flip the symbol backwards. And 6 divided by negative 2 is negative 3. It is a good idea to slow down when you have all these details to remember to do. Negative 2x minus 2 plus 2 is less than or equal to negative 4 plus 2. Cancel, cancel. Negative 2x less than or equal to negative 4 plus 2 is negative 2. Ooh, okay, so both sides have to be divided by negative 2. These cancel, x is isolated. My symbol has to flip backwards. Negative 2 divided by negative 2 is positive 1. Wow, let's graph it. I want a 1 and a negative 3 to show. There. I want circles on both of them, and in fact I know they're both going to be filled in circles because it's an or equal to situation. The numbers less than or equal to negative 3 are over here. I shade. The numbers greater than or equal to 1 are here. I shade. If I'm not sure, I plug in some values just to test whether this makes sense. Let's try 0. It's supposed to not give a correct answer when we plug it into here because it's not part of the answer. Negative 2 times 0 is 0, and 0 minus 2 is negative 2. The absolute value of negative 2 is 2. 2 is not greater than or equal to 4. So it's good that I did not shade the 0. How about positive 3? Negative 2 times positive 3 is negative 6. Negative 6 minus 2 is negative 8. The absolute value of negative 8 is equal to 8. 8 is greater than or equal to 4. That made sense. It worked. And it was shaded, so I'm happy. How about negative 4? Negative 2 times negative 4 is negative 8. Negative 8 minus 2 is negative 10. The absolute value of negative 10 is positive 10, which is greater than or equal to 4. I'm feeling confident in this answer. I can even try one of the numbers I have the circles on. 1. Negative 2 times 1 is negative 2. Negative 2 minus 2 is negative 4. The absolute value of negative 4 is positive 4. And yes, positive 4 is greater than or equal to positive 4. The or equal to makes this one work. Okay. That wouldn't have worked if we didn't have the or equal to. That's cool. But that's also a review. How am I doing for time? Pretty good. I only have a few more of these examples, and then I want to start talking about functions for a few minutes. So where am I? Yeah. I have another one. Doesn't look very different. But they always don't look very different. And then they end up being a little different. As soon as there's a slight detail that's not the same, you end up having to deal with something a little different. Absolute value of 2x plus 2 less than 2. Split 2x plus 2 less than 2. And 2x plus 2 greater than negative 2. Okay, lots of 2's. I think that's the reason I chose this example. Let's throw 2's all over the place and see if we can make ourselves make a mistake. I don't think we can. 2x plus 2 minus 2 is less than 2 minus 2. Oh, something interesting's happening here. These cancel. 2x is less than 0. Do I have to stop because I got a 0? No. It's a number. We're allowed to use the number 0 in this situation. We divide both sides by 2. It's not negative that we're dividing by, so we don't have to flip our symbol. These cancel. X is isolated. And of course, 0 divided by 2 is still 0. Will it happen over here? Are we going to get another 0? 2x plus 2 minus 2 is greater than negative 2 minus 2. No, we're not getting a 0. These cancel. 2x is greater than negative 2 minus 2 is negative 4. Divide both sides by 2. Cancel, cancel. Don't have to flip the symbol backwards, so it's still greater than. Negative 4 divided by 2 is negative 2. Interesting. Let's graph it. There's my 0. Need that for sure. I also want negative 2. Let's put circles on them. Let's take a bit more chalk. It happened again. I'm really going through the chalk. Where's that garbage can? Oh, it bounced out. Okay. I'll have to go and find that later. Stop Mocha from eating it. And here goes my chalk. Don't make it too long. Okay. So, I needed to put a 0 here. And I'm doing x less than 0, which means I'm shading this way. And greater than negative 2, which means I'm finished. I'm done my shading. And it's not or equal to, so I need the open circles. This works. It's fine. I'm not going to start trying to verify a bunch of these. Or should I? What about the 0? Let's try and verify the 0 in this. If x is 0, it should not give me something that verifies that's true because 0 is not included in the answer. 2 times 0 is 0, 0 plus 2 is 2, the absolute value of 2 is 2, but 2 is not less than 2. 2 is less than or equal to 2, but it didn't say less than or equal to 2. So 2 is not less than 2, so 0 should not give me a verification, and it didn't. So I feel confident in this. That's fun. The reason I put that one in was because I wanted to make the 0 thing happen because I thought it looked cool. One more, and then I'm going to get into some functions talk. And I'm going to look at the time, and I think my timing is good. We'll see how long I choose to prattle on about functions. Don't be afraid. Functions. Functions is fun. It has the word fun in it. Okay, how about negative 4x plus 6, all in absolute value bar, less than or equal to 10. It's all inside the bars, so I don't have to do simplification first. I'm splitting negative 4x plus 6 less than or equal to 10 and negative 4x plus 6 greater than or equal to negative 10. Be careful. Okay, algebra. Negative 4x plus 6 minus 6 less than or equal to 10 minus 6. Cancel, cancel. Negative 4x less than or equal to 10 minus 6, which is 4. Dividing both sides by a negative number. Cancel, cancel. Symbol turns backwards. 4 divided by negative 4 is negative 1. Negative 4x plus 6 minus 6 greater than or equal to negative 10 minus 6. Cancel, cancel. Negative 4x greater than or equal to negative 16. Dividing both sides by a negative number again. Interesting how when that happens, it happens with both. And when it doesn't happen, it doesn't happen with both. Interesting. Surprising? Maybe not. X is isolated. Symbol turns backwards. Negative 16 divided by negative 4 is positive 4. Yeah, I like it. It matches what I did earlier when I tried this one out. I'm going to graph it. 0, put the 0. 4 and negative 1 need to show. So negative 1 and 4. They're both are equal to, so they're both getting the solid circles. And less than or equal to 4 is over here. And the other one's saying greater than or equal to negative 1, so I'm shading in between them. I have my answer. It makes sense. I like it. This is fun. This has been fun. Now I'm going to talk about functions. Just a bit. Oh, all sorts of yakety yak. I'll try not to do too much of the yakety yak out loud. I'm going to read it and I'll see what I can say. Functions. What's the idea of functions? It's just worth introducing because we get to a stage in our math where thinking about functions, using functions language and functions notation becomes more and more useful. So, what is a function? Well, I told you already it has the word fun in it, so you know it's fun. I like to think of a function, and the way we use functions language, as like a little machine in a factory that produces some sort of goods. So let's review something that we were doing actually a couple of weeks ago. When we have an expression like 2x plus 3, well, we can plug in various values for x and see what they give. So let's see, we plug in these three numbers, 2, 1, and -3. Okay. Well, if I plug 2 into this, I get 2 times 2 plus 3, which is 4 plus 3, which is 7. If I plug 1 into this, I get 2 times 1 plus 3, which is 2 plus 3, which is 5. This is easy and fun. Okay, if we plug -3 into it, we get 2 times -3 plus 3, which is -6 plus 3, which gives -3. We have our answers. We're able to do this, and it's fun. And it's like a little machine. It makes me think of things that are mass-produced. And the idea that popped into my head is those little candies that are shaped like little bears. Sometimes they're red, sometimes they're blue, they're all sorts of different colors. Sometimes they have sugar coating on them. Sometimes the sugar is sweet, sometimes it's sour for some weird reason. And sometimes there's no sugar coating at all. There's all these different types of candy that can be made, but maybe they're all made by the same machine because the machine is making a shape like that bear. I like that. So the machine keeps working the same way, but the results keep on being different. Hey, like this. This machine keeps on working the same way. We're just doing algebra, simplifications with algebra skills, but we keep on getting different results depending on what we plug in. So imagine someone going to that machine that makes the bears and they plug in some food ingredients that are red, and then the machine starts producing red bears. They plug in some food ingredients that are orange and you get orange bears. Well, that makes sense, that there would be a machine that could make more than one type of bear instead of having to have a different machine for every one. So let's think about this idea of functions language and functions notation. Don't forget all of this. It's going to be familiar when we see how I do my next little example. We can just say that f of 2 is the result that we get when we plug in a 2. Just like the red bear-shaped candy is the result when we plug in red red ingredients. Okay, so f of 2. I've got to the end of that page. Take it away. That can be written like this. Remember? It's the same expression, except now it's an equation because I put an equal sign. And I'm saying what I get when I use that thing is a function of what the value that I plug in. So actually I shouldn't be calling it f of 2, not yet, because I didn't stick a 2 in there yet. I'll call it f of x, because x is a number and we haven't decided what that number is yet. But if we decide to plug in 2 like we did as our very first example before, well then this is going to become 2 times 2 plus 3. And we have gotten our machine to produce a different result because we decided to give it a different raw material. That being a 2 this time. 2 times 2 is 4, 4 plus 3 is 7. Well, this is looking familiar. It's the same thing that we got when we did it the other way. We're just getting used to this new notation. And that allows us to plug all of our information into a table of values. So I'm going to make a table of values. I'm going to have one side x, which is the x that I am deciding to plug in, like a 2 for instance, so x can be 2. And the other side, we call it f of x. It's the result that happens when a 2 is the raw material that was plugged in. And of course, we see that f of 2 ends up being 7, so we can just put a 7 here. And if I use the same values that I did before, f of 1 equals 2 times 1 plus 3, which is equal to 2 plus 3, which is equal to 5. I'm going faster now. And then that 5, well, if I put a 1 there, the 5 has to go here. And what was the other value I used before? -3. If I decide x is -3, then f of -3 equals 2 times -3 plus 3, which is -6 plus 3, which is -3, same answer we got before. and we get -3 as the result. So using functions language and arranging all of our raw materials and results into a table of values is useful. And that's why I wanted to introduce it. This becomes very handy when we start graphing shapes, because to graph shapes, we're going to want to plug more than one value into our little machine, which is our equation, and see what the results are so that we can draw a picture of the result. And with that, I think I have gotten to the end of my time and to the end of my lesson plan. So from Doug and from his very clever dog, who I have to return this book to so she can finish it, I would like to say thank you for being here. It was fun as usual, and I look forward to next time.